Welcome again. In this presentation, we will arrive at a desired region for closed loop poles. We will start with an error model. We will state conditions for rise time, overshoot and decay. We will arrive at overall requirement. We will compare our results with that of Astrom and Wittenmark. We will arrive at the desired transfer function. Let us start with specifications. We will assume that a step input is given in the reference signal R of the plant. We would want the output Y to have small rise time, small overshoot and small settling time. Of course, we would also like small steady state error. We have written Y of n, this is the plant output, this is E of n, which is the difference between the reference signal R and the output Y, and the reference signal has a unit step change. So as a result, the difference between R and Y is given here. This is the error signal. We would want E to have small fall time or small rise time for Y. We would want E to have small undershoot. We would want this error signal to settle fast, and we would want this error to go to 0 eventually. Error En of the following form satisfies the above requirements. En is given by rho n cos omega n, where rho lies between 0 and 1. When you take Z transform of this, you can show that the poles of E of Z will be at these two locations with radius rho and the angle omega. How does this satisfy these requirements? We will see in the next slide. Rho n cos omega n says that the initial error is 1. When I substitute n equals 0, I get En equals 1, which is 1 here, because we are talking about unit step. 1 minus 0 is 1. This also decays just like the error decays. There are oscillations in this signal, there are oscillations in this model, and the steady state error goes to 0. As n goes to infinity, this becomes 0 and hence En becomes 0. So what is the procedure? The user will specify maximum allowable fall time, that is how long it can take to reach this point, that it should be less than so many samples nr, and maximum allowable undershoot, which is this distance, should be less than epsilon. So it could be 1%, it could be 5%, it could be 10%, it depends on the problem that is getting controlled, it depends on the system that is getting controlled. And they can also specify the minimum required decay ratio. They can say that it is less than delta. So this nr, epsilon, delta are user specified parameters. Alright, once it is given, we will develop a method to determine rho and omega. This rho and omega are yet to be determined. So once we know that, we know the closed loop pole locations. We know En, then we can calculate the transfer function between the error signal E and the reference signal R. Maybe with that we can back calculate the controller GC. So this is the general approach. Now let us start with small fall time in error. So this is the same as the rise time in the plant output Y. Here it is fall time in the error. So we want to know when the error becomes 0 starting from 1. It becomes 0, that is En equals 0 for the first time when omega n equals pi by 2. So cos pi by 2 becomes 0. When I simplify, I get n equals pi by 2 omega. We want n to be less than nr. Recall, this is one of the user specified values. We substitute for n from here, pi by 2 omega less than nr or omega greater than pi by 2 nr. So this is the condition we have on omega. We arrived at from this requirement that the error should have a small fall time. We can plot it as follows. Omega denotes the angle. It is some large angle larger than a line whose angle is given by this pi by 2 nr. Next one is small undershoot. So in order to do this, we need to know when this E of n reaches the first minimum. We may be tempted to differentiate and equate it to 0, but this is not applicable because n is an integer. So let us look for a simpler expression. This expression reaches minimum when omega n equals pi, so that this becomes minus rho to the power n. So when I substitute En with omega n equals pi, that is rho n cos omega n with omega n equals pi, it becomes minus rho power n, and once again we have to substitute for n from here, so it becomes minus rho to the power pi by omega. So user specified maximum deviation is epsilon, so the absolute value of this should be less than epsilon, or we have rho to the power pi by omega should be less than epsilon. You have to remember this. In fact, I would want you to write this down. We are going to need this shortly. Now this can be written as rho less than epsilon to the power omega by pi, and that can be expressed in terms of this shaded region where we have assumed some omega and arrived at the value of rho. So the shaded region is the one that will satisfy this condition. So we already had one shaded region in the previous slide when we discussed the rise time in y or small fall time in the error. So we have two shaded regions. We have one more condition. Let us see what comes out of that. You have to remember, as I mentioned earlier, this expression, either this or what I have in red now. Let us take up small decay ratio. We want the ratio of two successive peaks to be small. If the ratio becomes small, then it will decay fast and reach 0 value quickly. Notice that the first undershoot occurs when omega n is approximately pi, and the first overshoot occurs when omega n is approximately 2 pi. We want this ratio to be less than some delta. So the first overshoot by first undershoot, the absolute value should be less than delta, and which would mean when I substitute and take the modulus, I get this expression. Cos omega n will go away. This should be less than delta. Now what is this delta? When delta equals 0.5, that is half, we refer to it as 1/4 decay, because from here to here it is half, from here to here it is half, and hence from presumably from here to here it will be 1/4. So half here, so it is 1/4. Similarly, if delta is 0.25, then it is approximately 1/8 decay. Typical values people specify are something like half decay or 1/4 decay. We never give such a large decay or such a small decay that it decays very fast. So 1/4 itself is quite acceptable most of the time. So 0.5, in any case we will not need more than 0.25. So anyway, let us substitute for omega n equals 2 pi from here. So n equals 2 pi by omega, which is the numerator, and so the denominator becomes rho to the power pi by omega should be less than delta. When I simplify this, I get rho rho to the power pi by omega to be less than delta or rho less than delta to the power omega by pi. Okay, I am going to write this down in the next slide. So this is the small decay ratio requirement. Recall the small undershoot requirement what I had in red, rho is less than epsilon to the power omega by pi. As I mentioned earlier, this epsilon is generally less than delta. For example, we might say overshoot to be 10%, 5%. 5% means 0.05 epsilon. If it is 10%, 0.1, 20% is 0.2, whereas decay ratio is usually 0.25 or larger. Remember, 0.25 itself is 1/8 decay. So typically this delta is smaller than epsilon. So usually epsilon is less than delta. As a result, small undershoot, if we satisfy this, it will automatically satisfy the decay condition required. So for both decay and undershoot condition, we have only one region. So let us summarize. The overall requirements are small rise time, small overshoot, and hence the overall requirement. So this is the small rise time, small overshoot. The overall requirement is as follows. We refer to it as the cut beetle leaf, which is very popular in India. This is the desired region we obtained, we arrived at by the current approach, whereas Astrom and Wittenmark in their book arrive at this region by discretizing a continuous domain result. Notice the similarity between this desired region and this desired region. Now let us arrive at the desired transfer function that satisfies this error model. When I take Z transform, I get this expression. I would encourage you to take the Z transform and verify that you indeed get this term on the right hand side. Now this is for the unit step input R of Z. So the transfer function between R and E is given by capital E by capital R, which becomes this after substituting for E and R as unit step. Now this Z and Z will cancel, I get this expression. One approach is to equate this to 1 over 1 plus GGC and back calculate GC. There could be some other approach as well. There could be another approach as well. What is the transfer function between reference R, Z and output YZ? This is the Z transform of R of n, which is the reference signal or set point. This is the Z transform of Y of n, the output. Now Ty of Z equals 1 minus Te of Z. When I substitute and simplify, I get this expression. This can be written as Z to the power minus 1 into C of Z inverse divided by phi CL of Z inverse. All that I have done is I have divided both numerator and denominator by Z squared to get an expression in powers of Z inverse. Because there is one extra Z here, it appears as Z to the power minus 1. We can use this to design controllers. One can see that this is the closed loop characteristic polynomial. We can use this to place the poles. One can verify that Ty of 1, that is substitute Z equals 1 over here, and verify that this is equal to 1. As a result, we see that there is no steady state offset between Y and R. We will use the closed loop characteristic polynomial to design the controller. With this, we have come to the end of this presentation. We will use this method as well as the methods we described in the videos of this week to design controllers in the next week as well as in the second part of this course. Thanks for joining. Goodbye.